Hello again. In today's session, we will start really actuarial mathematics. So we finished the review, we reviewed interest theory, we reviewed probability theory, and now we start taking on actuarial mathematics. So in this very short first session as a starter, what I will look at is trying to use random variable to look at age of death, or like to represent life of an individual. So what we will do is we will use just like, let's just start with this graph. So we'll have a graph age 0, and let's say this is the like the life of an individual or a life of machine, but we in insurance we are interested in life of an individual. So if this is the whole life, this is the time of death here, the whole life, this is the whole life, we'll use X, right? So this is the time of death, capital X. So X is the random variable that represents the whole life of individual, the random variable for death, like occurring at certain age, right? It's age at death, right? But sometimes we know that this is not age 0, we are at small x at certain age. Let's say the individual reach age 30, 40, and we are looking for the remaining lifetime. So what is the remaining lifetime? And this is, we're going to use different notation for this. What we will use is t. T is the remaining lifetime. Capital X is the random variable, or like age at death. T is also like age at death, but remaining lifetime. Right? So if you try to look at the relationship between them, so X, the big X, is equal T, the remaining lifetime, plus the small x. Small x is the age of the individual, right? This one. Right? And this is something we need to keep in our mind. So like x and t are random variable, but this is the remaining lifetime. And this random variable is the whole lifetime. And the whole lifetime, we are interested, like those random variables, to look at age at death, like age at death, right? And this is like very like basic concept. We looked at it when we looked at the review, but this is very important for us to remember it. So X is the full age and T is the remaining lifetime. Right? So what I wanted now to start is with some actuarial notation for what we discussed. Let's start with the X variable. T will come back to it. So let's look at the full life of an individual. So let's say we are looking at age 0. So we're evaluating at age 0. And we are interested of an individual dying before the age of X, the small x. Right? So we are interested like death. So I'll use this shaded area to say death, right? Death. So in actuarial notation, this one, what I'll just to see first how it's written, how it is in actuarial notation, and then you can also let me insert an image here just to make sure that you get it correctly. What does it look like? Okay. Do you see it? So what we, for this relationship, what I'm sharing here is X Q0. X is like small and 0 small, and Q is small letter, but subscript, right? So XQ0 here, it tells us exactly like this: for an individual at age 0. So an individual at age 0, what is the probability that he or she will die at or before age X? So for an individual age 0, or sometimes at birth, this tells us probability. What is probability of dying, or let's say death, before or actually at is included, or and at age 0, at age x, right? So this is the age of death, right? So this is very important to understand, which is a shaded area. In regular language, I mean in mathematical language, xq0, you can remember it's f of x, right? So which is the probability of death x occurs before small x, right? Simple, right? It's something we need to keep it in our mind, right? This is the first notation we introduced today. So this is like the mortality, right? The opposite of mortality is the second notation we wanted to introduce now is also we use actuarial notation, but instead of mortality, but survival, right? So the survival function here, let me get it bigger so you can see it. Wanted the first time to use images, so at least you get the correct shape of the notation, because my handwriting is bad, but also you can review the textbook to read it through. But xp0 is the opposite. So xqx, if you remember that an individual age 0, death occurs before age x. Now this one is individual age 0, this is same age 0. What's the probability that they survive to live after age x? Right? What's the probability to survive to age x? So x is not included because here it's survive, right? Survive to age x. So death happens before x. So the relationship between xp0 and xqs, you can understand it in simple way. xp0 is equal to 1 minus xqx, right? xq0 I meant, right? They are the opposite, right? This is something we need to keep in our mind. Oh, maybe I need to let me write it, right? So they are, but xp0, given that you understand it here like death occurs here, so somebody needs to survive, it's actually, this is s of x, our friend s of x, survival function, right? So let's take one example also like to understand, but we need to understand it that this is the death occurs before age x, and this death occurs after age x for somebody age 0. Later on we will alter the age. Instead of making age 0, we can have different ages. But for now, because we're looking at x, the variable x, we're not looking at the variable. Remember what we said? We're looking at this one. Later on, when we look at the remaining lifetime, we will introduce different age, right? So let's take one example. And remember here what we are looking at is age of failure, right? X, what is x? X is just, remember, it's random variable, represents age at failure. Remember always this. So x is represented for somebody's age 0 is represented by uniform distribution, is uniformly, and we did something like this. When we reviewed the statistics, we looked at this, right? Let's say between age 0 and 100. So x is a random variable represented by x random variable that represents age at failure, and we are using uniform distribution to describe this life. So this life is distributed uniformly between 0 and 100. So if we want to do x q0, right, and this will, because it's uniformly distributed, remember what we said, this is f of x, right? F of x, we understand it, we already did it. For uniform distribution is x over 100 for x distributed between 0 and 100. We are now dealing with continuous distribution, so equality or not equality, it doesn't matter. For continuous distribution, you can use equality or without equality, right? And if you want to do xp0 for the same life, uniform distribution, this is represented by s of x, which is the opposite of this one, is 1 minus x over 100, right? So what if, let's say, for example, the question asks you for an individual age 0, what is probability, what is the probability for her or him, let's say her, to survive to age 60. So we need like the probability for somebody age 0 to survive to age 60, right? And in notation, here is survive, right? We need to read carefully. So survive is px, so p0 because at age 0 to survive to age 60, so 60. Oh, let me use the same color. Oh, so here age 0, you need to survive, the individual to survive to 60. So death occurs after, right? So survive to age 60, right? So, and how is this? It's normal distribution. We know we know the general form xp0 is s of x, which is the general form is 1 minus x over 100, and this will be 1 minus, because surviving the age 60, it's 60, so it's 60 over 100. Simple enough to say it's 0.4, right? And what is now 60 Q0? And this is the opposite now. Death occurs between 0 and 60. So what's the probability that death occurs between these years? This is f of x, right? This f of x, which is x over 100, which is 60 over 100. It gives us 0.4. And these, they add, oh, sorry, 0.6, they must add up to 1, right? Simple enough, not much of complication here. What if we dealing with, you know, like those are common distribution. Another example, example 2. Now x, and remember, always when we talk about x, age at failure, right? Age at failure, just remember, at failure, random variable, is now exponentially distributed. For exponential distribution, it's not over a period, because exponential distribution can go forever, but it's usually you need to get within mu, the rate of death, right? Rate of mortality is constant for, let's take 0.05. So like for this life, it's 0.05, mortality rate mu is 0.5. And the question is, what is the probability for, and what's the probability for as a new birth to die before age, let's say 60? And this is, we need to look at it, it's die before age 60. So we are looking at the mortality function. It's so we are looking at Q because it's at birth, a new birth, and now we're looking at 60. And this is a f of x, and this is something we need to memorize it for. You don't need every time to integrate, or it's simple. It's just you need to memorize the exponential distribution, uniform distribution. Those are very important functions to remember. So f of x is 1 minus e to minus mu, which is 0.5, multiplied by x, which is 60. Right. I use always my calculator, same calculator, just get used to it. So we have e minus 0.05 multiplied by 60. It's 1 minus 0.04978, and if I subtract it from 1, so for death to occur between this period is 950213, right? So what is the probability now? What if we wanted to calculate the same one, 60p0, the probability to survive? And this is probability to survive. This is S of x, sorry, S of x, right? And x is 60. So simply in this one is easier to calculate. It's 0, 5 multiplied by 60. But since we already calculated here, it's, well, I mean, you can do it again, but same one, right? Take the rate of 50 and 60, so it will be the same one here, right? 0, 4, 9, 7, 8, right? Does that make sense? It's simple. Simple. And if we want to look at the relationship, just like because uniform is quite important, the uniform and exponential distribution. If you look at S of x, like, or let's go S of x here. And remember what's S of x is survival function. Here it's P0x. And this is x. What is x? Is age at failure. Remember, this is the random variable. We look at age at failure. If we start with uniform distributions like this, and for our function, if uniform between 0 and 100, but this is 0 to 100. So, sorry, the death occurs here at 100, everyone will die, 0. If you look at the other one, the exponential distribution, it should start from here, right? Yes, if you put 0 in your survival function here, it will give you 1, right? Anything raised to 0 is 1. And then it declines quickly, and then started slowing down. It doesn't hit 0 here. It goes, because this is it's uniform distribution, but gets closer to 0, right? And this is exponential, and this one is uniform, right? It should be straight line. If not straight line, it's because my handwriting skills is so bad, right? So you see the relationship. Exponential distribution is rather goes quickly at the beginning and then slows down, right? Doesn't. But if from here, if you want to take the properties of survival function, because all we deal is about survival functions, what we study in actuarial mathematics. So first property is, if you take S of x at x, let's say when x equals 0, like surviving at birth is 1, right? You start with 1. The second thing, so it's not any function we can use it as survival function. It has to to have certain properties for us to consider it as survival function. The second one is S of, or let's use the limit. When x approaches infinity, you know, when like the age becomes very, very high of S of x, and this one should be 0, right? So the survival function is bounded between 0 and 1. The limit in the will be 0, right? This is what make it survival function. Let's take a few examples also, like just to get ourselves used to these. What I will do also, we'll take the concepts, finish like this whole class, not this class, I mean with the few sessions on the survival models. Once we finish survival models, you will have lots of problem sets. I'll post them for you guys, but we'll do at the end maybe like some questions, review with the questions. But we'll go over concepts with simple examples. Later on we'll take lots of harder questions. And also you need to do as much as you can of the problem sets that I'll post for you. But just like a simple example here, you know, we are sometimes interested in calculating probability of death. You know, if you looking at insurance industry, is always interested of like for life insurance is the probability of somebody dies at certain age, you know, when they price the product they produce. And sometimes it's for the other the opposite of this one is the longevity risk that if you insure it through insurance, like, or maybe social pension, or pension, is you are interested in an individual to survive. because as long as they survive, they get benefit. So the calculating probability of life surviving and or probability of death are very important for us. We'll come back to those two products as we move on. But let's look at probability calculation of some probabilities using survival model. So we are interested of X occurs between A and B. Remember what is X? X is the random variable of at failure, random death, or like the contingency to occur. So, and this one, we have the life 0. We're still working with age 0. Later on, we'll alter it. You have A and B. So somehow death occurs here. Right. I will use this kind of notation whenever I shaded an area. It means that death occurs there, right? So probability of A bounded between X bounded age of death between A and B is, you can think of it as mortality happens less than B, and subtract from it mortality happens less than A. So it's f of B minus f of A. In actuarial notation, this one will be, we have a Q because we're dealing with F with the mortality Q0, and death happens at B. Subtraction Q0, death happen at A, right? Alternatively, you can say this one, instead of doing this, you can say, well, somebody survived to A, you subtract from it surviving to B. So this can be looked at as survival of A minus survival of B, right? The difference between them. In actuarial notation, this one B will be using P0, and now A, we subtract from it P0, B, right? And survival, the smaller X usually have a, or not usually, should have a higher probability, right? Because surviving smaller age should, like have a higher probability, right? Does that make sense? So if you take, for instance, one example, let's take one example. Let's go back to our function of X is exponentially distributed with mu, the rate of mortality. Some textbook you use lambda, that will use mu, but it doesn't matter. As if it's defined, you use whatever notation they call it. But mu equals, let's say, take the same 5%, right? The death rate occurs at 5%, right? And we are interested in calculate the probability of death. Death is represented by X between 1 and 2. Right? We are interested in this one. And this is, if I visualize it here, 0, 1, 2. You can calculate it by mortality, happens less than 2, subtract from it mortality happens before 1. But because exponential distribution is easier to deal with survival, because survival easier to deal with, I will take this minus this. So it will be S of 1 minus S of 2. And S of 1 in exponential distribution E minus mu, which is 0.5, multiplied by 1, subtract from it E minus 0.5, multiplied by 2, which is E minus 0.05 minus E minus 0.1, right? If you use your calculator, quickly, I got about 4%, slightly more. Yeah. Does that make sense? It's straightforward, it's clear, right? Let's take another example, because usually we use also, again, like I'm repeating the most, if you write actuarial exams, most functions actually, or not most, many questions, they have uniform distribution or exponential distribution. So it's always good to get yourself familiar with memorizing all, like the, not the calculation, but rather those models, like really repeat lots of examples using them. And as well, we will build other questions using harder functions. But let's say now x is uniformly distributed between, let's take the same age, 0 and 100, right? Yeah, I mean, you can find the probability of death occurs between, let's say, 40 and 60. It doesn't take much of effort. This one is straightforward, right? Because its uniform distribution should be 20 over 100. But just like to look at it in this picture, death occurs here, right? So easier here is to take f of x. So we take this one, subtract from it. So it will be f of 40 minus f of 60. Right? If you do that, it's remember the f of x is for this one is x over 100, right? So it will be 4. Sorry, make a mistake here. I meant, sorry. It's always good to correct it in the sense, like the function itself, it will help you to correct if you make a mistake. Let's take the mortality. It's easier, right? So we take f of 60 minus f of 40, right? So if you take f of 60, what is f of 60? Is 60 divided by 100. Subtract 40 divided by 100, it will be 0.2, which is, I told you before, we calculate uniform distribution, you can calculate it right away. This is 100. What is this in comparison to the rest? Is 20 over 100. So it's straightforward. Next class will also take on a new notation, but I think for now this is just like to introduce like two notations, px or p0, xp0, xp, xq0. Those are very important notation that we'll use them extensively and a lot throughout this course. All right, see you later.